Folks, Dr. Kamakoti needs no introduction. He is a very senior professor at IIT Madras and has a whole list of awards and accomplishments to his, which I will not go over. But the most prominent, which is very interesting for us, is the Shakti microprocessor and the whole environment that has been created around it. Thanks to you, Dr. Kamakoti, and your team for joining us here today. We are looking forward to your talk and interactions over the day. Over to you, sir.
Thank you very much. I have with me Dr. Neil Gala. So we both will be introducing the RISC-V, which is one of the most prominent emerging instruction set architecture. Today being adopted, as we are talking, adopted by many multiple MNCs, that have already invested themselves in their own processors. For example, some of the processor giants like AMD and Intel, everybody today have started looking at RISC-V. We believe that this is going to be the architecture for the next generation. And it is very important that every curriculum across the globe in computer organization and architecture must include RISC-V, or should RISC-V be taught in that. So in this direction, I'm also very grateful to the PES for inviting us in this winter school on computer architecture and giving us half a day to talk about RISC-V. And we'll certainly give an introduction to this RISC-V. And then we also would like to follow up with all the participants who are part of this particular winter school through many things like internship or projects, etc., which are oriented towards RISC-V, so that we build a very good RISC-V ecosystem in the country, which should be extremely useful for the country in the times to come. Both from an individual career perspective and from a economy perspective, and also from a security perspective. This expertise is of very great importance. With these few words, I will now go into so what I'll be doing. So I have Dr. Neil. I must tell him he is my PhD student. He completed PhD with me, and then today is an authority in RISC-V. He knows more RISC-V than anyone else in the country. Probably he is one of the top RISC-V researchers in the world. That much I may say. Proudly, I would like to say that. So what I will do is to basically introduce instruction set architecture and bring you to a stage where you will all appreciate what RISC-V is, a need for instruction set architecture like RISC-V. So that is the point where I will stop, and then I will leave it to Neil to continue that and take you forward on the RISC-V education on the RISC-V, right? So with this, let me just start. Neil, can you go to the next slide?
Yeah.
Yeah. So when you look at computer architecture, you have 5 layers. The first layer is the digital hardware, the lowermost layer. And then this digital hardware exposes an interface called a micro instructions. Micro instructions are, suppose you are saying that you want to read 2 registers and add it and store the result back. So it will, in an assembly language, it will be add R1, R2, R3, right? And now this add R1, R2, R3 is composed of many micro instructions. The first micro instruction is to fetch the values of R2 and R3 to the input of the ALU, then instructing the ALU to add, and then storing back the result back to, say, R1. So there are 3 micro instructions that are involved while you want to do a one assembly instruction. So the digital hardware provides an interface, what you call as a micro instruction as an interface. Now, on top of it, there is a layer which you call as a micro programming layer, right? So what is an input to the micro programming layer is is the assembly language instruction. So add R1, R2, R3 come to the micro programming layer, and the micro program for that add R1, R2, R3 is executed by the digital hardware. Now, beyond the assembly instruction, there are two layers. One is operating system, another is the compiler layer. So the operating system basically interacts with the with the microarchitecture. It does many things with the microarchitecture. So, for example, the operating system is responsible for setting up the page table. The operating system is responsible for setting up the interrupt service routines. The operating system is responsible for, flushing out, doing the context switching. So all the activities that the operating system you study in a normal operating system course are basically an interface to the microprogramming level. Similarly, you have the compiler. So the compiled code basically executes on the microarchitecture. And again, the interface to that is the ISA, the instruction set architecture. So what does a compiler do? It basically takes an application program and compiles it into the machine language or your assembly language. And the assembly language is again executed by the digital hardware. So, and then of course, the last level is the high level or programming or your application program, right? So what you see is a layer of virtual machines. When you write your C code, you never bother what is the compiler or what is the architecture in which you're going to execute, right? So you need not bother. So you just write your C code and ultimately it gets executed on the architecture. Never you have actually bothered in your first year when you do an introduction to programming course, you have never bothered about, what is the architecture, what is the compiler, what is the version of the processor, and you write printf, what is the operating system, nothing. So there is a virtual machine that is given to you. As far as you are concerned, that virtual machine will understand the C language and it will execute it for you. How does it understand? There are multiple layers below that. So there is a compiler, there's an operating system, then there is a microprogramming, and then a digital hardware. But all those things are kept virtual to you. Similarly, as a compiler, I don't really care. I only know about the assembly language. I just take the code and convert it to an assembly language. I don't really bother how that assembly language instructions are going to be executed, right? Similarly, operating system, right? So for all these purposes, you see that the ISA becomes the application binary interface between your uh, applications, your operating system and compiler, and the microarchitecture. And that is where the instruction set architecture, the ISA, becomes extremely important for you. And the robustness of this ISA, the simplicity of this ISA, we'll also talk about something called extensibility of this ISA, is very crucial for you to build a compute ecosystem ranging from what you call as embedded systems. Then you have mobile, sort of laptop, mobile, desktop type of systems. Intermediately, you also have, say, certain controllers like your point of sale terminal, etc. Then you have your laptop, mobiles, etc. And beyond that, you have your servers and other sort of systems. So you have a family of microprocessors that are necessary. And it is very interesting that if you can define one instruction set architecture that can spawn across this family of microprocessor, then that is something very useful. And that will be something which will make the entire compute stack very robust and versatile. So when you look at computer architecture, it is a very highly structured computer architecture. It has these 5 layers. Each of the layer is a virtual machine. And there are 3 virtual machines above the microarchitecture. And the way these 3 virtual machines interact with the microarchitecture and get their programs executed and the functionality realized is through this instruction set architecture. And the ISA becomes extremely crucial. And so that is the takeaway from this slide. And the ISA must be used for a family of microprocessors, starting from embedded devices to microcontrollers to mobile phone, laptop, desktops, to high performance servers in the cloud. Okay, so this is the problem in hand, and how are we going to address this? Next.
Yeah.
So I want to ask to the audience, somebody can on their mic and tell me what is the difference between computer organization and computer architecture as a course? What is the difference?
Sir,
Somebody can
computer organization deals with the much basic, like, what's RISC-V, and I mean, not what is register read, what is register write, what is IO. Computer architecture is a bit more advanced, like branch prediction and all these stuff.
no.
So computer architecture deals with the microarchitecture, like the making of a chip, I mean the internals, and organization means the various levels associated, like operating system, compilers, and the low-level hardware.
Then you have a course on operating system. What is the difference between computer organization and operating system? If you say computer organization deals with operating system and compilers, etc., but then why do you have a separate course on operating system?
Sir, computer organization is more of the circuit design side, like the
Organization is circuit design, then architecture is?
architecture would be the addressing modes, and I guess about the registers part.
No.
They both are almost same.
They both are same. Then why do you have two courses? Just to fill up credits?
No, one for low level and other for high level.
What is
I think.
low? What is high?
So
Means
architecture is functional.
in computer architecture we study computer organization from the high level view. Means how different modules are connected together and how the whole computer will work. But in organization we study about how they are interfacing. But in computer architecture we read what is going inside them.
Okay, so your answer is somewhat close. So computer organization basically talks about the interface of the operating system, compilers, and the application programming to the architecture, right? So what are all the features that the architecture must support so that it makes the life easy for the compiler, operating system, and the application program? This is precisely what computer organization teaches. Computer architecture teaches how those features are actually implemented, right? So, for example, we say that there is an add instruction that is necessary, right? And so how is the interface for that happening? It happens through this ISA, right? So then architecture says, what sort of adder should I use? Should I use a carry look ahead adder or a carry ripple adder, right? So that is an architecture topic. Computer organization basically teaches that you need to execute this instruction. Computer architecture basically teaches how fast can you execute this instruction. For example, I can do pipelining, right? So this is a computer architecture topic. Organization basically tells you that we need these type of addressing modes. Why do we need these type of addressing modes? For example, why do I need an indirect addressing mode? Can you tell me? From anybody can tell me, why do we need an indirect addressing mode? Why is it in the ISA there is an indirect addressing mode is something like giving a memory address through a register. So I say add R1 comma within bracket R2. So if R2 is 1000, load R1 comma bracket R2, and say if R2 is 1000, that means I say load the content of 1000 into R1. Right? So this is called an indirect addressing mode. What is the need for an indirect addressing mode?
So pointer to take data from the memory.
Loading
Number
data
of,
from memory is one point. Specifically, the other answer is correct. So I want to implement pointers in C. Now, if I want to implement pointers in C, I need an indirect addressing mode. So the computer organization basically needs to expose these needs why the ISA has certain things. Why is it that, if you take the Intel architecture, the way there are some 256 ways of basically addressing memory. There's a matrix. It's called mod RM SIB byte. Okay, so if you can look into the Intel developer manual, you'll find that, right? So why do we need these type of things? So there should be an explanation given, and that explanation is what computer organization basically teaches you. Computer organization should teach you ISA. In my opinion, computer organization should teach you ISA as a part of your instruction set architecture. It should not just, many curriculum will tell how to add two numbers. That's an assembly program. Still, we'll go off to the old Gaonkar 8085, 8086 book. And many curriculums across India has that. I also, as a professor in a leading institute, I feel very bad that still we have not done anything to upgrade the syllabus. Though I try much, very, very difficult to get the universities to agree to this. But no, what should we teach now today? We need to teach something like how to write an assembly. So you should, in the computer organization course, we should talk about how do you set up paging in an architecture, right? Which register you have to set, which memory you have to set. How do you set a page table? How do you create an exception, and how do you handle exception? So, right? So these things are some of the things. How do you ensure segmentation? How do you switch from a machine mode to a supervisor mode to an hypervisor mode to a user mode? So these are all topics that need to be, and once you teach it, that then only when somebody goes to an operating system course, they say round robin scheduling, and the CPU does that. So how does a round robin scheduling be? Can you implement? How can you implement a round robin scheduling? So we need to understand what a timer interrupt is. We need to understand how to set time quantum. All these things are underlying uh, operating system concepts which are to be realized in the hardware. And hardware should have certain facilities for the operating system to realize what it wants. And that is precisely the topic, subject content of computer organization. And so what is needed and how is it enabled through the ISA, the instruction set architecture, is the only content of computer organization. Computer architecture says that, okay, you need so many things. You have committed so many things to the ISA. How do I implement it effectively to meet certain power considerations, to meet certain area consideration? I want a very small chip. It should consume less power. At the same time, it needs to, it needs to perform very well, right? My timing has to be very less. My frequency has to be very high. So I need this power area timing, right? PAT, we call it PAT. Now we need a good PAT chip which will implement whatever we have committed to the ISA. And that topic becomes computer architecture. So to just give you, this is, since we are talking of computer organization and architecture, PAT is a very orthogonal thing, right? So if I want a very limited power, either and a lesser area, my timing will suffer. For example, carry ripple adder versus carry look ahead adder. It's a very simple example, right? Your carry look ahead adder consumes a lot more area and power, but it is very fast. If you want to add n bits, you can do it in log n time. But if you are using a carry ripple adder, it consumes less area and less power, but it is very slow. It takes n time. So if I want to add a 264-bit number, it is 64 stage delay for a carry ripple adder, while it is just 2 power 6, right? So 2 power 6, 6 gate delays, so 6 unit delays for a carry look ahead adder. So these type of decisions come as a part of the computer architecture. So understanding the ISA becomes the core important aspect of the computer organization course. Next slide, Neil.
Yeah.
So ISA, the instruction set architecture, helps the higher layers implement their desired functionality on the underlying hardware. And this is what we term as a application binary interface. Okay, next. right? So now let us go and look at, I want to talk about, since we are talking about RISC-V, I want to spend a few moments talking about CISC versus RISC, right? First and foremost, there are 5 stages in the execution of the instruction, right? So what are those 5 stages? Can some audience respond? What are the 5 stages in the execution of an instruction?
Instruction fetch, fetch, decode, execute, memory, and write back.
Memory and?
Write back to the
And
registers.
write back. Okay. So there are 5 stages. So you fetch an instruction, you increment the PC, that can be a single stage, then you decode that instruction. And the next stage that we do is, after decoding the instruction, we go and fetch the necessary data for that. Then we execute that instruction and store back the results. So these are 5 stages, but this can be merged. Some of them can be combined, and so that is one part, how to realize. But essentially, there are at least minimum 5 stages in the pipeline. So we call it as a pipeline. Why we call it as a pipeline? Can somebody answer that?
Because they are
They are
sequential.
implemented sequentially.
Why we call it as a pipeline? Sequentially, one
Because
after
one
another.
instruction follows the other,
Yeah.
like in a
So,
pipeline.
yeah. So exactly. Good. So essentially, it means that more than one instruction can be on the fly, right? So I'm fetching instruction 1. When I'm decoding instruction 1, I can fetch instruction 2. When I'm fetching the data for instruction 1, I can decode instruction 2. I can fetch instruction 3, right? This essentially implies that the hardware necessary for each of these 5 stages are independent, right? Meaning are independent in the sense are different. So your microarchitecture will have 5 different hardware, each doing exclusively one of these activities. There'll be a hardware which is fetching the instruction. There'll be a hardware which is decoding the instruction. There'll be a hardware which will be executing the instruction. There'll be hardware which will be fetching the data. There'll be a hardware executing the instruction. There'll be a hardware responsible for writing back the result. Each of these hardware are independent. So when one hardware is working on one part of the instruction, one part of one instruction, the next instruction can be fetched and it can be processed by the previous stage. And this is how pipeline happens in your automobile also, right? So there'll be one fellow who will be assembling, another fellow will be fitting tires, another fellow will be putting the light, another fellow will be pumping air, like that, right? So there's a pipeline. So at any point of time, there can be multiple instructions at different stages of the pipe, right? Now you understand that there is a decode, right? All of us have understood about one translation. Like, what is that translation? The compiler's translation. It takes a C program and it gives you an assembly instruction. But then there is one inherent, another, implicit translation that happens, where the program, the assembly program, is again decoded into a set of signals, which we call as micro instruction, by the decoder, right? So the decoder takes the assembly instruction and interprets that assembly instruction, and it finds out what it needs to do. So there are 2 translations that are happening. One is an explicit translation that is done by the compiler. Then there is an implicit translation that is basically done by your decode unit, right? Now, if your implicit translation that is happening in the decode unit is simple, or then it is basically called a reduced instruction set computer. If the implicit translation that is happening is complex, that means it is called a complex instruction set computer. Okay, so the RISC versus CISC is the complexity of the decoding which is happening implicitly inside your hardware, right? So very simple thing. So if you are trying to learn a book, right, you have 100 concepts, then it takes more time than 10 concepts, right? Suppose I'm giving you a book which is, say, 5 pages, each page having 2 concepts, versus 50 pages, each having 2 concepts. Obviously, what will be easy for you? Which will be easy for you? Somebody can answer. The 5 pages with 2 concepts, right? So essentially, uh, so if I have lesser number of instructions, then it is easy for me to decode versus large number of instructions. So that is the first intuition where you say, I will have a reduced instruction set. Okay, so I have a reduced instruction set, which will be lesser number of instructions rather than a complex instruction set, which will have large number of instructions. But then this doesn't solve the problem, right? So I give you 5 pages where each concept is an NP complete problem, while I give you a 50 page where each concept is a a simple binary arithmetic problem, right? So obviously the complexity is not just on the number of instruction, but also on how complex is it for us to understand that instruction, right? So what do you mean by understanding the instruction? So one is the format of the instruction, right? Now, when Neil is going to cover the RISC, he'll talk a bit about the format of this instruction, right? Now, every instruction, so the first thing in the format is whether I have, yeah, what is the length of the instruction, right? Every instruction is of the same length. It's a very, very simplified format when compared to a RISC where every instruction can be of variable length. For example, if you look at x86, the Intel and AMD, you could have instructions that are 1 byte to instructions that are some 80 bytes. So what happens is when I fetch something from the memory, I don't know. Before I decode, I even don't know whether I have fetched a full instruction or I have fetched more than one instruction. Right? I don't know whether I have fetched more than one instruction or I have fetched only half of an instruction. Even to find out the instruction boundary, right? Even to find out the instruction boundary in a RISC architecture, in a CISC architecture, that instruction boundary finding hardware itself will be as complex as the entire fetch plus decode stage of a RISC architecture, right? So because that is very complex. So essentially, now what a RISC architecture essentially means that we need to have a decode stage, which is very easy, which is very clear. And one of the important thing is that every instruction will be of the same length. The next thing that we are also looking at is in every instruction, we have source operands, we have destination operand. We should know what the instruction is, whether it's add or subtract or multiply or call or some. And we should know where to find the source operand, where to find the destination operand. The position of these things in an instruction. So instruction is say 32-bit or 64-bit. The position of where I can find the source register, where I can find the source operands, where I can find the destination operand, where I can find what the operation is. The exact position of this, those are also sort of fixed in the case of RISC. Right? This cannot be fixed in the case of CISC because you have variable lengths. So we don't know really where what is. But in the case of RISC, these are all fixed. So when I know that these are all fixed, the decoding becomes easy because the moment an instruction comes, I could have multiple things happening with that instruction because I know where the source operand is, where the destination operand is. So I can start fetching before I find out what the operation is. So this enables a sort of a small implicit parallelism, but small but crucial parallelism in the way I decode these instructions. So that is also very, very important. So that is basically the RISC. So to sum up, the takeaway from the slide is there are two implicit, two translations that happen. One is the language to the instruction set and the assembly, and another is from assembly to the micro signals that happen. The second implicit translation happens in the hardware. And now if that translation, if it is going to be easy, then it is a RISC. If it is going to be tough, we call it CISC. And to make it easy, we have fixed length instructions and also fixed formats for the instruction. Format essentially meaning where I can find the operands, where I can find the operation, where I can find the different aspects of an instruction, which will have operands and source operand, destination operands, and the operation that we want to do. So this is what, so the RISC-V architecture is a RISC architecture. And when the ISA is being introduced, you will find these things quite clear regarding the format, regarding the length of the instruction or the size of the instruction as we proceed in today's morning lecture sessions. You will realize the importance of that. Okay, next, Neil. Neil?
Yeah, there's a little lag.
That's a lag. Okay. Now let us go and look at assist. This is just a thing. One of the 2-byte instruction that were there in Intel for quite some time, which was ASCII adjust before division. Okay, AAD. And that 2 bytes does so many things. He adjusts to unpack the BCD digits. The least significant digit is in the AL register, and the most significant digit is in the AH register, so that a division operation performed on the result will yield a correct unpacked BCD value. The AAD instruction sets the value in the AL register to AL plus 10 into AH, and then clears the AH register to 0, 0. The value in the AX register is then equal to the binary equivalent of the original unpacked 2-digit base 10 number in registers AH and AL. So this is what 2 bytes does. So the hardware, after looking at these 2 bytes, have to do all these things. So that is what I give you a feel of the RISC, right? Now let us go and look at the next RISC instruction. Neil, go to the next slide.
Yeah.
Neil, so this is the killer call, right? So there's a call instruction. The English description of the functionality of the call itself is 5 pages. The English description. Then you write a pseudocode for it. Then you write a program for it. Then you write a microarchitecture that is going to implement this, right? So I just don't try to read this. I just wanted to show the bigness of this. So what you see, I've just taken it from the Intel Developer Manual. Now what you see is this call instruction. There are varieties of call, and the English description is what you see on the right-hand side here. Next slide. So it goes from this slide to next. Neil? Can you change this? Yeah, this fully, right? I have put it in some 2x reduction. Next. So the RISC glories, quote unquote, are that they are variable instruction length. The decoder of x86 is 10 times complex than a 3-stage RISC-V processor. Now, a 3-stage RISC-V processor in BlueSpec was written in 2 days, completely working perfect. Okay, so a decoder of x86 is 10x complex than a 3-stage RISC-V processor, and then you have multiple addressing modes. For example, it is base plus scale into index plus displacement, and your scale can take 0, 1, 2, 4, etc. So can somebody tell me why we need this type of a complex addressing mode?
Maybe for branches.
This complex addressing, base plus scale into index plus displacement, why do you need it for branches?
So for different segments, because x86 has base segment.
Why segment is just an address? Segment is just an address. So base plus whatever. See, the segment register comes before that. So this is addressing within a segment. So I have DS colon, DS is data segment, colon, base plus scale into index plus displacement. So this is basically a logical address before adding the segment base.
Because some of it might not be word aligned.
Can you tell from a compiler perspective or a programming language perspective, why do you need that such complex addressing mode.
So because of memory management.
Stride access.
Memory management, that one malloc. Memory management is done from operating system.
Strided access, sir.
Why strided access? Can you give a can you give a much more clear example from a programming language perspective? One thing is I'm trying to access arrays, right? Right? Arrays will be in the segment, so don't confuse with the segment register there. The base of the array starts at some address. Okay.
So if we have something like a tensor in for AI application, then
No.
we
Don't
want
go
to
to
change.
those tensor and also no. We should give very simple examples. That's the way. Don't understand computer architecture with tensors. Okay. Very simple thing. Let us say I have an array. Sorry. Yeah. Please tell me.
Executing multiple instruction same time.
You are talking about an addressing mode of a single instruction.
Sir, is it like a 2D array or something for?
It is a simple array. Let us start with the array.
Okay.
Okay, it's a simple array. Array has a base, which is where A0, right? 0. Now, base will be stored in the base address. And if I say A of I, it will be the address where the 0th element is added plus the index I. But then, if it is a character, it is 1 byte, right? And x86 is a byte addressable memory. So, for different objects, so I can have an array of records, I can have an array of whatever. So, that scale will become scale into index, right? That scale will basically become whatever the type, right? I need not have index at all, but I can have in index, in character, it is 1. If it is a short int, it is 2. It is a thing, I can have 4. So I can go 0, 1, 2, 4. And then there's a displacement, right? Displacement, why I need a displacement? Base plus scale into index is useful for, say, accessing an array. A of I is base address where A0 is stored. It is not a segment address. It's a base address where A0 is stored. You do malloc for A, there will be a base address, right? That will be in the base, right? Plus, if it is a character array, your scale is 1 and I is the index, right? You are doing A of I, right? If it is a short int, your scale is 2. If it is a long or it's just an integer, scale is 4. Okay, 4 int index. But why do you need displacement? Can you give an example for where you need a displacement? So suppose I'm having a record.
If we want the lower, sorry, sir.
Right? Suppose I have a record, right? In the record, so the A of I dot something, right? So suppose I define a structure and I put an array of that structure. So a structure can have, say, 3 integers. It is, let us say I'm storing points, right? Ij. So a structure will have an array of points, right? So then when I want to access the first point, it is the displacement is 0. When I want to access the second point, assuming it's a floating point, single precision, the displacement will be 4. So this base plus scale into index plus displacement can be used to store an array of structures where base will be the start of that array, scale will be the size of that each element, but I have a limited option there, and I have index. Index will be whichever I, and using that base plus scale into index will tell me the starting address of the particular element, and within that element I have to keep moving. So there'll be multiple fields within each element, this being a structure. So for that I use displacement. So what I'm trying to say is, when the Intel addressing modes were conceived, these type of addressing modes were included into it because there is a need ultimately from a programming language. So whatever I see in an ISA is something that has been introduced, not because that fellow liked it, right? Why did you introduce? So there's a question that say, why should I have such a complex addressing mode? The reason is, motivation for that is it is driven by a programming language to basically include such type of addressing modes. So that is the very, very important thing that we need to keep in mind. Now, when we look at the RISC-V, we don't have such complex addressing mode, right? Because we want to keep the decoding very simple. If I have such a complex addressing mode, I will not be in a position to have fixed length instructions. I could not fix where the operand and the operation, the source operand, destination operand. I cannot fix the format of the instruction. So that'll be it will become extremely difficult. And there are, of course, other things also that makes it complex in the RISC, right? So RISC will not have this type of addressing modes. That means what? It makes the life of the compiler difficult, while RISC makes the life of the compiler easy. So life of the compiler easy, while the decoding, the implicit translation that is happening is difficult, is the RISC era, right? Making the life of the compiler difficult, while this decoding becomes simple, that is the RISC era. Okay, so the difference between RISC and CISC, this is something that we have to look. So as a drawback of RISC, right, what we have encountered is I make the life of the compiler difficult. That means what could have been coded using this addressing mode now needs more instructions by the compiler to realize what I want. Because I just basically have one address there, a register with an address. So that register should be filled with this computation of base plus scale into index plus displacement. And that should be put into that register so that you access the correct memory location. So this computation of base plus scale into index plus displacement is not done by the hardware. It is to be done by the compiler by executing multiple instructions before you actually calculate the address. So address calculation becomes extremely important in this direction. Sorry. So given this type of RISC versus CISC, now the other important thing is, since I need to start calculating these address, etc., but the compiler has to have specific instructions, assembly instructions to calculate the address and put it now, which could have been directly done by the hardware in the case of CISC. The size of the executable in the case of RISC can be larger, right, versus CISC. Now, when that is larger, when the size of the executable becomes larger, and then we start using these RISC processors in embedded systems where there is a limitation in the amount of memory I can use, and if the executable size is larger, then there is an conflict there, right? So I need to have lesser memory in my embedded system, but the RISC actually gives me larger executables. So there is an orthogonal sort of conflict. So as you see, if all these conflicts doesn't exist, then we don't actually have a living, right? As computer architects, we survive on these type of conflicts, and so we welcome this conflict, because this actually basically gives us more work to basically see how effectively I can write a compiler so that the size of the executable is limited, right? So is reduced. So how I do compiler optimization. So the RISC compilers have more scope, no, or more need. I don't say scope, but there is a need for optimizing the size of the executable from the RISC perspective, because of certain the limitations that the hardware possesses by not having such type of fancy or much needed, sometimes needed addressing modes and related instructions. Okay, so next.
Yeah.
Yeah. So to just sum up, the RISC features are fixed length. So you can do a lot of concurrency in decoding, right? As I told, because you know where different operands and operations lie. And but the compiler issues are large size executables. This is a trade-off to embedded systems, really or not so really, that we will see. And that is crucially depending on the compiler writer and the optimization that we can do. But as of now, embedded systems do have RISC architecture. So the compilers have done a good job. And so the success of such RISC architectures in the embedded platform and also now up to the server platform, essentially trying to realize that family of microprocessors that we are talking of stands testimony that RISC is much better than CISC. It is always easy to handle things at the software level rather than pushing it into the hardware level. So that is where the success of RISC-V is going to be in place. Okay, next. So now we must also, before I hand over to Neil, let me also talk about a very interesting thing which many curriculums today leave it off. I think all of you who are attending this, please note down NAND to Tetris. NAND 2 is numeral 2 to Tetris. That's a course. So I have offered this in the NPTEL platform as elements of computing or foundation to computing system design, FCSD. One of this elements of computing or one of this, I forgot the name of the exact name I gave there. Okay, I think it's elements of computing. Okay, so kindly look at nan2tetris.org, and there is a course. You can basically self-learn it. It's not very difficult if you are at the. But we teach it for the third semester undergraduate fellows. So that is a very wonderful course. Now you need to undergo that course, it starts with a NAND gate, then it defines a microarchitecture, it defines a machine language. Then, so all these things you write using a language very close to Verilog. You actually make the machine, and then there is an assembler. You write an assembler which will take the machine assembly language and convert it to binary. Then there's a 2-pass assembler. Then we introduce something called LVM, the low-level virtual machine, LLVM, which is stack-based LLVM. So you translate that LLVM instruction into assembly language. You write a translator. Then there is an abridged Java. You write a complete compiler. And that compiler will take an abridged Java type of language and convert it to LVM instruction. So finally, the Tetris game, right? Many people know the Tetris game. The Tetris game is coded in that language. It's called Jack. It's an abridged Java. Now you use your compiler to compile it, to translate it to the LVM. Then you use your translator again to translate that LVM into assembly. You use the assembler you have designed to translate that assembly instruction into machine, and use the machine that you have created in Verilog. You input these machine instruction, see the execution. So this entire stack is being introduced, and this can be done in 20 hours. Okay, and that is what we have achieved. This is there is a book by Xiaomi, I think. So is the author, and all these tools are available on the net free. So I think all of you should do this course. Any computer science or electrical or any person claiming to do something with computing should do this course. It's a very excellent course, very interesting course. So do that. So at this point, why I talked about that, there is something called an LLVM. No, I don't know. And none of the curriculum across the country is introducing LLVM at an undergraduate or postgraduate level. Unfortunately, it's very, very important. What is this low-level virtual machine? A low-level virtual machine is a layer between the high-level programming language and your assembly language. So LLVM will be a set of 4 to 5 instructions, or maximum sometimes it can be 10, 15 instructions. The LLVM that you will see on the NAND to Tetris is just 6 instructions. So it will be a limited set of instructions. And what you do is you write an interpreter that will convert that LLVM to assembly. Now, what will happen is that when new languages come, so you started with C, then you went to R, then you went to R sharp, C sharp, and C++, then Java. So you have multiple programs, Python, Perl, Lisp. So you have multiple languages. Every compiler writer should write a compiler which will convert that the language to LVM. They need not write for your binary, right? So all these major languages have a translator which will take the language construct and convert it to an LVM level. Now, your translator will take that LVM and execute. This means any programming language, as long as they have a translator which will translate to the LVM, that language can ultimately start executing on your machine. So this two-level translation, the two-stage translation, where LLVM to binary, high-level program to LLVM, this gives you a very interesting issue on portability, right? So very quickly you can make your architecture portable to any programming or vice versa. Any language, new language can be ported onto your architecture very quickly. So the need for understanding LLVM is very, very crucial for the market today. I think in India, we have hardly 100 people who can work at an LLVM level. And I encourage all the participants today to start deeply looking at LLVM and start seeing how that is going to be. It's a extremely crucial stuff for any computer architecture and systems programming development. Okay, next.
You want me to go to the last slide or?
This is the next one. So and other important thing about the ISA, which should be taught in an assembly language curriculum. I want the PES and all the institutions and the teachers who are there, who have autonomous, can frame their syllabus accordingly to look at this very seriously. What is taught in the assembly language today is how to fly a helicopter or whatever. So add 2 numbers, multiply 4 numbers. No, that is not the thing. So what we need to do here is if you look at the RISC file, as Neil will be introducing, you have 4 modes: the user mode, supervisor, hypervisor, and machine mode. Okay. So why there are 4 modes? Because your operating system also works in 4. There is a user mode. The machine boots up in the machine mode. Then there is something called an hypervisor mode. Then there is hypervisor. There are many things that we can do from a security angle on the hypervisor. Then there is a supervisor mode. So if people would have worked on, in my opinion, real operating systems like Linux, right, Unix, you know that there is a SU, super user, right? And then there is a normal user. So whatever you do at the super user, roughly, I'm not saying one-to-one mapping, will be executed on the supervisor mode. And then there is a user mode. So typically your operating system itself will have different programs, one working on the machine mode, the different parts of the operating system, one working on the machine mode. Some part of the operating system will work on the hypervisor, some work on the supervisor, some work on the user mode. Now, each one has its own privileges. For example, the machine mode has the highest privilege. There are certain instructions which can be executed only in machine mode, but not in hypervisor mode. And more interestingly, I can also, the microarchitecture allows you to define memory segments which can be accessed only when you are in some particular mode. So I can have a segment which is accessible only in machine mode. That means the user, supervisor, and hypervisor cannot access it. So these are all extremely important from a security perspective. Not only security in terms of cyber hacking, etc. Even between process to process, inadvertently or accidentally, one process should not go and interfere with a memory of another processor, right? Process is a program in execution. So one process should not go and accidentally go and change or convert the thing in the other process. So this is something extremely important for us, right? So these are the things that should be taught in an assembly language course. How do you go from one level to another level? And how do you understand what a microarchitecture can do at a particular mode, right? And these are some things. We have a very, very interesting assembly language lab. I request all teachers who are here to basically get in touch with us, and we will give you even the complete structure of this assembly language lab, which you can start pursuing, and that will give deep insights on how that will give you deep insights. Sorry, that will give you deep insights on how you start basically addressing the operating system issues, right? So this is something which the ISA also supports. ISA supports these levels. What do you mean by supporting these levels? The ISA specifically defines what could be done in each of these levels. Specifically defines the access that could be enabled. ISA also specifically describes certain registers which can be used to implement this type of a layered architecture wherein the operating system can be mapped. Different functionalities of the operating system can be mapped onto these type of layers. So that is also something that, as a part of our RISC-V, we will basically elaborate. Next.
Yeah.
That slide is not changing for me.
Yeah.
Yeah. So in addition to the modes that we have started, the ISA also supports virtual memory. So many of you should know what a virtual memory is. The virtual memory is that as a compiler, as a programming, as a program, I see a 4 GB address space, though the physical memory will be only 2 GB. Right? So this is the notion of a virtual memory. Now, how is virtual memory implemented? It is implemented through using paging. Right? So paging is a concept which is used for doing. It's called demand paging also. So the success of virtual memory is when I'm executing the program, it is enough if I ensure that the next instruction that I need to execute and the data needed for the next instruction to get executed, if that is available in the RAM, I can proceed. Right? So whenever I'm executing a process, at any instance of time, the next instruction to be executed and the data needed for the next instruction to execute, if those two are available in the RAM, it is sufficient. So it is not necessary that when I start executing a program, I need to load the entire executable onto the memory. And that leads to the concept of virtual memory, which is also very important. So ISA actually supports paging. How does an instruction set architecture support paging? That is something that should be part of your assembly language lab. And if that's not there, then it's useless, right? So you don't understand the system's programming at all. And so that is also something which Neil will cover in the RISC-V stuff. And the next one is there is also something called physical memory partitions. We call it PMP. And this is basically gives you a notion like segmentation, where each of these physical memory partitions can be assigned a privilege level. As I told in the previous slide, there are 4 privilege levels. So we can assign a particular privilege level for each of this physical memory. And then based on that, the operating system is now given this physical memory partition as a facility. So it can assign privilege levels to each of these partitions so that the necessary security, the necessary type of protection that it wants to offer to the memory can be realized here. See, all the hacks or all the damage are done because of memory access. So if I'm going to control the memory properly, then the system can become secure and robust. Again, security is not just an external cyber hacking or cyber attack, but it is also something like inadvertent, access of data by one of the processes already executing. It accesses the data of the operating system or another process. It can be inadvertent also, but those things have to be checked. And that is where the physical memory partition becomes very, very important. Next. And more importantly today, I have a system for agriculture. I have a system for medicine. I have a system for AI, edge AI for a mobile. These processors, each of these processors need different types of instructions, right? Today, bit manipulation instruction is needed for storage devices. Okay, so as and when you are evolving a family of microprocessors, one of the next generation research in microprocessor or next generation commerce in microprocessor tends towards having what we call as domain-specific architecture. For the biology domain, the type of servers I need is different from a transaction processing domain where I have databases, right? In an embedded system, the thing that I need for agriculture may be different from the thing that I need for, say, a camera, because I need more image processing there. There I need more sensor processing at the agriculture. In the camera, I need image processing. So we need multiple instructions at each level. And so essentially, your ISA should be extensible. What do you mean by extensible? I should be in a position to add a new instruction without disturbing the decoding of the previous instructions, existing instruction. So I need to add without touching those. There are a set of instructions already encoded. Now I have to add a new instruction, and I should quickly come out with an encoding for that new instruction so that in a way that it doesn't disturb the existing instruction. That means what? First thing is I have to add a new hardware and my decoder design becomes easy. The decoder now finds a new operation. Okay, route it to this. So I need not touch the existing units in the architecture. I need to add a new unit, and the decoder will easily find out because it's extensible. The old decoding is not changing. A new part comes in, the decoder easily finds out, and it finds out, okay, this is the new instruction, and you can go and use this, right? So my hardware designs become easy. More importantly, my software also becomes easy because your compiler, the one which actually converts your into assembly, and from assembly to binary, your assembler need not get changed from a bit encoding part. Like assembly will translate into a binary, right? That binary encoding doesn't change, and that becomes really a plug and play type of an ISA. And so other important thing that we are going to get from the RISC-V, it is an encumbrance-free BSD licensed ISA. What do you mean by a BSD license? Is that you take this instruction set architecture, you go and do some changes, and you make a system. You need not report back what change you have done. There are open source where there are something called GNU public license, GPL licenses, where if you make a change, you have to report back. In this case, you need not even report back. So that means it becomes extremely useful for protecting our intellectual property, etc. Like you can take this instruction set architecture, you can take the entire tool ecosystem, etc. You can do your change and you can make your own system. You need not tell what you have done. And that is something very, very important, very, very democratic about the RISC-V architecture. And the other important thing is today accelerators. Right, all of you might have learned about GPUs, etc. Right, they are accelerators which will do your functionality faster. So the RISC-V also gives you a way by which you can design your own architecture, and you can design your own accelerator, put it as a peripheral, and there are very systematic way by which any computation you want to do at the peripheral can be routed to the peripheral, the functionality done on the peripheral, and the results got back from them. So this is also very important when we are looking at a domain-specific architecture. So wherein that we can add new instructions, we can add new accelerators, we can make these, we can change the software to use these accelerators effectively, very quickly, and also, and these are all facilitated by having what we call as an extensible instruction set architecture. Okay, next.
That's also.
Yeah. So thank you very much. Any questions to me before I hand over to me?
Excuse me, sir.
Yes.
Yes. Would you say that computer organization is essential to computer architecture, or are they two separate domains?
Computer organization and architecture are two extremely intertwined twins, right? So one cannot exist without another. Computer organization should precede computer architecture in a curriculum, and the trust that you want to put in the computer organization course would be more on the ISA and the way the ISA interacts with the operating system and compilers. and all the lectures and the labs should be oriented towards it. While the computer, and more or less the computer organization should be a lab-oriented course rather than, learning something. And then the computer architecture is the way you implement those concepts, and that should be that should be succeeding the computer organization course, right? I have a very different view with whatever is happening in the general curriculum. So my recommendation is, in the third semester of your undergraduate, you do NAND to Tetris, and then start working on this stuff on the assembly language, and then succeed it with computer architecture. And when you are doing the computer architecture, you can also do the operating system together. The operating system, there is a course, not this normal junk, right? So there is a course on XV6 offered by MIT. That is the real operating system course, right? And that will create the system programming environment. Today, every industry today is struggling even to have a good Linux administrator, okay? And so that is the bigger thing. But we are creating so many engineers. The real skill set is not coming out. Skill set is not just skill, but it's also that we need to understand the system in its full perspective. I think followed by this XV6, all of you look at XV6. There's a RISC 5 for XV6. It's an abridged Linux, and based on that abridged 8,000 lines of code, based on the abridged Linux, MIT has given a course. So we should start looking at that course in great detail, right? So if you do that type of a curriculum, I think systems programming will thrive very nicely. And that is what it means to understand systems, okay? Not the junk that we are doing currently. Sorry.
Excuse me, sir.
Yes.
Sir, can you please elaborate more on the LLVM part?
Yeah, LLVM is basically a level. So suppose I have a structure, right? Directly converting a C program with involving structure to directly into an assembly RISC level assembly is going to be extremely difficult, right? So LLVM actually becomes an intermediate level, right? Intermediate level in the sense that from a programming language construct, to see what is an equivalent LLVM program is much easier than actually seeing what is a ultimate binary program. Right? There is a sort of a one-to-one conceptual mapping between an LLVM instruction and the assembly and this high-level programming, and that makes the job easy for the RISC, because RISC is not giving you a lot of facilities which the CISC gave. So the compiler will be struggling to take a normal programming construct and directly converting to this would be an extremely difficult task for it. So that is where LLVM becomes extremely important. LLVM gives you one level of abstraction between the assembly language and the main programming language. So, and that abstraction is much more oriented towards programming language rather than the machine language. So the compiler will be, it's very easy to write a compiler which will take the programming language construct and give you another program which is in the language of this virtual machine. A virtual machine, what is the LLVM? It's again a language. So you take a C language, so you have hello world.c, it becomes hello world.vm, then it becomes hello world.asm. So the C to VM is done by that translator, VM to ASM is done by another translator. So this two-stage translation makes life much simpler, and also we can involve a lot more of optimization at the L. From the VM to ASM, I can put a lot more optimization so that I get reduced binary size, etc. Those type of optimization will be much difficult for me to evolve when I directly convert .c to .asm. So to cut the entire story short, instead of converting from .c to .asm, I do from .c to .vm and then do from .vm to .asm. And both these two-level translations make the compiler's job much more peaceful than directly attempting from .c to .asm, right? So this is an answer I can give you now. Now, for you to realize this, see, these things are something like, how Indian philosophy describes, ultimate reality, right? Indian philosophy describes moksha as something, is ultimate reality, as something you can only experience, right? You cannot define it. So similarly, this also, you can only experience, and the way you experience is do the NAND to Tetris course, right? And you can take guidance from the NPTEL lectures I have given. There you will really appreciate how it would have been a hell for you to write a compiler directly from the jack to ASM. But if by introducing this LLVM, the whole process becomes much easier. Like in 2 to 3 hours, you can write that compiler, and 3 hours you can write this next translator. So that is the story here. Okay, so that is the use of LLVM. Okay.
Yeah. Good morning, sir. My question is like how this extensible ISA or this domain-specific architecture can be helpful in preventing the some of the latest hardware-based attacks in modern processors.
Oh, no. So the extensible ISA has nothing to do with attack. The hypervisor mode, I think, Neil, we are working on a very, very interesting notion of what we call a separation kernel. A separation kernel is a software layer that separates the operating system, that isolates the operating system from the underlying hardware, right? And this separation kernel will enable you to monitor what the operating system is trying to do with the hardware. And there is something called an high assurance boot, which will ensure that your separation kernel cannot be tampered with. Okay, so this is the entire story. Now, the hypervisor mode that we are talking of in this 4 modes is now becoming extremely crucial to give you a highest level of security, wherein somebody cannot hack into a system, install a rootkit, or install other things by which they can manipulate and use the execute instructions that are not actually permissible or that have malicious intent. Okay, so the security actually comes from the hypervisor mode and the supervisor mode. To give you at a very, very low level, the security basically comes with the fact that the microarchitecture supports multiple layers, multiple privilege levels, and that each privilege level has certain privileges, and the architecture ensures that those privileges are not violated, and that basically gives us this entire story. Okay, so this is something that we need to keep in mind. Yeah. You got it?
Yes, sir. Thanks.
Okay.
Okay.
Yeah. There are no more questions. Thank you very much. I hand it over to Dr. Neil to take it forward. Neil.
Thanks, sir. Yeah. Hello, everyone, and very good morning and a happy new year to everyone on this call. So I think Prof has given a very, very motivating reasoning and justification as to why ISAs are important and what are the different types of ISAs, what you can do with ISAs, and how it affects the entire stack. And what I will be talking about for the rest of the session today is specifically about the RISC-V ISA. There are 2 major categories of ISAs today, 2 major categories of specific